In this set of lecture notes, we're going to talk about uncertainty and error analysis. So this discussion is obviously extremely important for physicists and engineers, perhaps somewhat less important for chemists, and maybe even less important for, let's say, medical doctors and biology professionals, but it's still not going to hurt to consider all of this. And since most of students in this class are going to be engineers and physicists, this is of utmost importance. Now, this is a lot more pertaining in this class to labs, not so much to lectures and not so much to problem solving, but since we are going to be doing labs and I'm going to ask you to do some error analysis in labs, it's going to come in handy. So I'm not going to write this down, but first thing that we need to answer, first question that we need to answer is, what is error analysis? And so I'll give you an example. When I make a statement, I have exactly 4 chairs in my room. That's an exact statement, right? I mean, I can go to my room, count the chairs, and hopefully I have no problem counting till 4. So that's going to be an exact statement, right? It's something that I can count. Another example would be something like 2 times 5 equals 10. That's also an exact statement, right? Yes, we can make all kinds of jokes that sometimes it doesn't work and so on, but in reality, that is an exact statement. So the statements that are exact, we would not have to make error analysis for, because, well, there is no error. 4 chairs is 4 chairs, and 2 times 5 is 10. So we don't have any issues with that. However, in a lot of situations, especially in laboratory setting, when we're making measurements, the values that we get as our measurement are not exact. So in such a case, we would have to figure out how not exact they are. In other words, what is the error that we make in making this measurement? So I'm going to start by introducing 2 terms that you probably already know from other classes. Let's define accuracy and precision. A lot of times in everyday language, people tend to mix these 2 terms up or use them interchangeably. Obviously, in physics, we cannot be mixing those terms up. We cannot be we cannot use them interchangeably because they mean different things. So accuracy is defined as proximity of measured values or value to the quote-unquote true or accepted value. Okay, and precision is proximity of measured values to each other. So the best way to represent these 2 terms is by visualizing, sorry about that, is by visualizing a target, a bullseye. So this is the bullseye here, okay? So imagine I have this target and I'm going to throw darts at this target. So my goal, my quote-unquote true value, is to hit the bullseye, right? That's what I'm aiming for. So let's say that I throw a bunch of darts and I hit the target like so. Not quite at the bullseye, but pretty close, right? So this is what I would call high accuracy. Okay. I'm going to draw another target here. I'm going to repeat this experiment. So again, I'm aiming at the bullseye. This time I'm going to hit the target like this. So this is the situation where the values are really close to each other, but not close to the desired value. So I would say that this is high precision, but low accuracy. Okay. And finally, I'll do one more here. So here is my bullseye. Okay. Now I'm going to throw the dart like this. So this would be high precision and high accuracy. Okay. So every time that you're analyzing experimental results, not just in this class, but going forward as well, and not necessarily only in physics, but in other disciplines as well, think about not just getting the quote-unquote the right number, but also how reproducible your results are. So imagine this target, this dartboard. Imagine throwing the darts at this target. Okay. Now there are a couple of ways to analyze your results numerically, also in terms of accuracy and precision. And I bet you know those as well, but let me write this down anyway. So accuracy is comparison to the true value. Okay, so a lot of times we talk about it in terms of percent error. So percent error is defined as the measured value minus the true value, the actual value, the accepted value, whatever you want to call it, divided by the true value and multiply that by 100%. Okay, so I'm going to box this because this is one of the equations that we're going to need in this class. So again, percent error is a comparison to the true value. So if you kind of have an expectation of what the outcome of an experiment should be, then you can analyze your data as comparison to that expectation. Notice that percent error is a positive number always, because you are taking the absolute value effectively of the differences between measured values and the true values. For precision, we can write sort of a similar equation. So here we're comparing values to each other. So we're going to call that percent difference. So percent difference is defined as the difference in two values. Oh, I'll call this value 1 and value 2. Find the difference of those, absolute value of the difference, divided by the average of the two values. Or maybe there are more than two values that you're measuring, then you're going to be dividing by the average of all of those. We'll talk about that in a minute. And then also multiply this by 100%. Okay, so I'll box this again. So here we don't have an accepted value. We're just trying to determine what the outcome of the experiment is. So we're comparing values to each other. Again, notice that both of these calculations should lead you a number that's greater than 0. So when analyzing outcomes of laboratories, please make sure that you don't give me negative percent errors. Okay. So then I'll briefly mention here types of errors. So where does that percent error or percent difference come from? I'll briefly mention it here, and then I'll post a separate handout on Canvas that talks about what exactly different types of errors are. So the two big categories are random errors and systematic errors. Okay, so notice how there is no such thing as human error. We will, again, kind of talk about that as we go through the labs in this class. But every error that you're making in the measurement falls into the category of either random or systematic error. So in order to get better results, we should minimize errors. So we can minimize random errors by using statistical analysis. We'll talk about that briefly in a second. By using statistical analysis. Okay. And systematic errors we can minimize by repeating the experiment under different conditions. So again, I'm going to post a handout that talks about all of these different types of errors. And here I'm only going to mention that systematic errors often or most often arise from either conditions of the experiment itself or due to the state and conditions of the instrumentation, as in devices that you're using to perform the experiment and to make the measurements in the experiment. Okay? Furthermore, this particular situation or this particular idea that no instruments are perfect leads to what we call experimental uncertainty. Okay, experimental uncertainty. So even if you can minimize or get rid of the great majority of the other errors that can occur in the course of experimentation and the course of measurement, you will never be able to completely get rid of experimental uncertainty because no instrument is perfect. So let me give you an example. Let's say I take a ruler, and this is going to be a very poorly drawn ruler, so you can probably find a better picture or visualize a better ruler, right? So let's say that we have a ruler and we're measuring length of something. Let's just put this in centimeters for now. Okay, we're measuring a length of something. So here is how I'm going to measure this length. So this is my little object that I want to know the length. In fact, why don't I start this at 1, so pretend that there is more to this object, because we can use these values in the future. Anyway, so let's say that I want to use this ruler or this portion of the ruler to measure an object. Okay, so I'm only showing you the end piece of this object. So depending on how you're going to read this ruler, you can say that the length of this object is 1.7 centimeters. But is it exactly 1.7 centimeters though? Well, not really. In fact, if you kind of zoom in and you look at where this edge of the object falls, it doesn't fall on exactly that little line. And yeah, sometimes it does, but in this case it does not. So that means that we can actually get an extra digit, an extra decimal place in making this measurement, but that extra digit is always estimated. Sorry about that. Okay, so this is an estimated digit. So I'm going to say that this is 1.75 centimeters. So I'm estimating this last digit here. Just one. Okay? So basically, what I'm saying here is that this ruler is not perfect, right? So there is only so many decimal places that I can get with this ruler. There is absolutely no way that I'm going to measure, the length of this object with a basic ruler and have it something like that. That just doesn't work, right? You laugh at me even writing this, I hope, because, well, we know that ruler is not that great of a measuring instrument when it comes to that much precision, to that many decimal places. So that last digit is going to be estimated, okay? So that's where that experimental uncertainty comes from, the fact that you always have to estimate the last digit. So the way that we do this is we take the smallest division on the measuring instrument and divide it by 2. Now, in digital instruments, we actually typically don't divide by 2. So in digital instrument, we usually just take the smallest division. So here on this ruler, this is not a digital instrument, obviously. This is an analog instrument. So I'm going to say that the smallest division here on the ruler, on this one, is 1 millimeter, right? So experimental uncertainty, that I'm going to call delta x, or delta length, if you want to call that, is going to be 1 millimeter divided by 2, so half a millimeter. If you're not familiar with this symbol, this is a Greek letter delta, little delta. Okay, don't confuse it with other symbols that are similar to it but not quite the same, such as sigma and so on. So make sure that you know how to properly indicate this. So what I'm saying here is that this is the experimental uncertainty in me measuring the length of this object with this ruler. Okay, now I mentioned digital instruments, so let me just do it over here on the side. So obviously I'm not going to be dealing with digital rulers, although there are such a thing. They're called digital calipers, but let's not worry about that right now. So I'm not going to worry about digital rulers, but let's say I'm measuring a mass of something, and let's say I get 124.6 grams as a mass of something. So the smallest division is right here, right? So it measures mass up to 0.1 grams. So experimental uncertainty in mass, I'm going to use M for mass. We'll talk about that later. Okay, experimental uncertainty in mass is 0.1 gram. So I'm not going to divide that by 2. Okay, so this is typically how experimental uncertainty is determined. So for the analog instrument, you divide it by 2 because you have to estimate that last digit. And for digital, you usually don't because, well, the instrument itself estimates that last digit. Okay, sometimes kind of depends on what you're reading as far as who is doing the uncertainty analysis. Sometimes people don't divide smallest digits by 2 at all. Sometimes people divide every smallest digit by 2. regardless of whether it's analog or digital. So this is kind of what I do, but as for future experiments, use one or the other. Okay, but make sure that you're consistent with how you're using this. Okay, so let's say that I'm going to go back to my ruler here, my length of the little measured object. Now I need to somehow represent the measurement, right? So here's how I'm going to do this. So I'm going to report experimental value. So it's going to be value plus or minus the experimental uncertainty in that value. I'll write it like this, okay? Value plus or minus experimental uncertainty in this value. So there is a couple of pointers that you have to follow when you're doing that. So for example, I wrote down the length of this ruler as measured in centimeters, but I wrote the experimental uncertainty in millimeters. That's actually a no-no. So when you're reporting experimental values, the units have to match. So here's how I'm going to write it. I can write it as 1.75 centimeters plus or minus, I'm converting the uncertainty to centimeters, or I'm going to convert the value to millimeters and then leave uncertainty in millimeters. Okay? So the units have to agree. Pick one, stick with it. And furthermore, the number of decimal places. The number of decimal places between the value and the uncertainty have to agree. Now, units-wise, we already talked about how important units are, right? So you can also write it like this. Put the units after the fact. That's also perfectly fine. But again, the value and the uncertainty in those units still have to agree with each other. Okay? So in the labs where I'm going to ask you to talk about uncertainties and errors and such things, keep this in mind. I will be very carefully looking for consistency in reporting experimental values. Okay, so units have to agree, and the number of decimal places between the value and the uncertainty have to agree. So that one for measurement of mass in the upper right, I would write as 124.6 grams plus or minus 0.1 gram. Okay, so the plus or minus, it's actually not a part of the uncertainty itself, but basically what it says is that the value could be that much bigger or that much smaller based on how imprecise the measurement is. Okay, so if I'm taking one of these values, I guess I'll just stick with my length here. So I'll do it in centimeters. Basically what I'm saying is that the minimum that this value can be is 1.70 centimeters. And the maximum that this value can be is 1.80 centimeters. So the true value of the length of that little object is somewhere between 1.70 centimeters and 1.80 centimeters. And remember that last digit is estimated, right? So it's 1.7 something centimeters. Okay? So keep that in mind as well. Now, sometimes when we make measurements. Sometimes we need to make more than one measurement and then calculate something based on the measurements that we made. So I'll give you an example of that as well. So what I'm going to do is use just some super basic equation. Distance equals rate times time. We'll talk about this equation later. It's actually not really correct when it comes to physics. There is a better way of writing it, but let's not worry about that. So let's say that I can measure distance, and I can also measure time, and I need to calculate the rate. Well, you probably did a problem like this somewhere in 2nd or 3rd grade. Okay? So I'm not worried about you being able to measure distance or measure time or whatever, or perform the calculation. Right now, I want to concentrate on specifically what happens with uncertainties and errors. So let's say that we measure distance to be 15.5 centimeters with uncertainty of 0.3 centimeters. Let's not worry about how we make that measurement. Time is 2.5 seconds plus or minus 0.2 seconds. Okay, so these are our measurements. Okay, well, when we're making a calculation, well, obviously R is going to be distance over time. That part is simple enough. What we all know how to do is to calculate what's called a nominal value. So nominal value would be calculated from these guys, from the actual measurements. So these are also called nominal values. Okay, so I would do R equals D over T, which is 15.5 centimeters divided by 2.5 seconds. So I'm going to put that in my calculator and get 6.2 centimeters per second. Okay, well, in principle, you should also think about sig figs here. So we already talked about sig figs, right? So for division, you're going to use the smallest number of sig figs. 2 sig figs. Okay, so everything's fine. Proper units, no problem. So that's the nominal value. But the thing is that both distance and time were measured not perfectly, right? So we had this experimental errors in measurement, right? We had this experimental uncertainties. Okay, so I'm going to call this value delta D. That's my experimental uncertainty in distance. And I'm going to call this value delta T. That's my experimental uncertainty in time. So those values are going to, or excuse me, those uncertainties are going to affect how good of a value I've just got for calculation of rate. So one of the ways to do that is, again, to think about minimum and maximum. So I can figure out minimum value of R by taking the smallest possible distance and the largest possible time. Now, that combination of minimum and maximum variables depends on how exactly this calculation is done, right? So here I'm dividing two numbers. I'm dividing distance by time. So if I want to minimize that calculation, I want to put smallest number possible in the numerator and largest number possible in the denominator, right? So I would calculate R min. How would I get minimum distance? Well, I would take that nominal value and subtract the uncertainty, right? So my minimum distance would be 15.2 centimeters. And for maximum time, I would take the nominal value and add the uncertainty. So this would be 2.7 seconds. So again, I'm going to plug this into my calculator. And remembering sig figs, I'm going to round this to 5.6 centimeters per second. Okay. So then let's do the same thing for maximum value of R. I would get maximum value of R from the maximum value in the numerator and the minimum value in the denominator. So I would get R max, so I get distance max by adding uncertainty, so 15.8 centimeters. And I get minimum time by subtracting uncertainty, so 2.3 seconds. Again, I'm putting this in my calculator and rounding it to 2 sig figs, 6.9 centimeters per second. Okay. Now, I have to report what I found, right? So if the purpose of this experiment was to calculate the value of R, then I have to somehow put all of this together. Well, I have this nominal value of R. That's all nice and good. And yeah, that nominal value lies between minimum and maximum, right? So I have to somehow estimate its uncertainty. Now, there are different ways of doing that. So for my calculus class, calculus-based class, we're going to go through this process that's called propagation of errors, but obviously that requires calculus. So for my algebra-based class, and even in calculus-based class, we can do kind of a quick estimate of what the uncertainty is, right? What we can do is we can subtract these two values. So I'm going to do R max minus R min and divide that by 2. Okay, so I'm going to use rounded numbers here because as far as I'm concerned, this calculation can only be done to 2 sig figs, right? That's how my measurements were made. So I'm going to find the difference of these two numbers, 6.9 minus 5.6. Then I'm going to divide that by 2. And then I have to make sure that I am consistent with the decimal places. So if I actually did this, I got 0.65 centimeters per second, of course. But that's not really good because it doesn't agree in sig figs. So the thing is that for uncertainty, always round up if you have to round. Okay, so I'm going to report uncertainty in R here as 0.7 centimeters per second. Okay, so then my answer would be written of this form, R plus or minus delta R, right? So I would report it as 6.2 centimeters per second plus or minus 0.7 centimeters per second. So again, this is kind of a quick and dirty way of estimating uncertainty based on uncertainties of measurements. Okay, so keep that in mind for some of the labs that we're going to be doing in this class. Last thing that I want to show you right now is a little bit of statistical analysis. So if you hate statistics, don't panic. We're not going to do everything you ever learned in statistics. I just want to show you a couple of tools. So a couple of ways that you can figure out how good your measurements were, especially when you have repeated measurements. Okay? Repeated measurements. So use statistics. Okay? Again, don't panic. I'm not going to do a full-on statistics lecture, just a couple of quick things. So let's say that you're measuring some value x, and you made measurements that you're gonna call x1, x2, x3, x4, and so on. And you're going to make a total of n measurements. So I'm calling capital N or little n, it really doesn't matter. I'm calling that the number of measurements. Well, I'm sure you know how to do the average. A lot of times in statistics you will see it written as x bar, okay, x bar. So that's the average value. Well, we're gonna add all of these measurements together, however many there are, and divide by the total number of measurements. Okay, so this can also be written as the sum of all the measurements. So I here stands for ith measurement. I hope that you all know this notation. So this here means summation or sum, right? So when I write it like this with an I in the subscript, it means that I'm adding every possible measurement that I can imagine up to the nth measurement, right? Because I have n total measurements, and then I'm going to divide that by n. I kind of made a mess out of this equation, so let me rewrite it without extra nodes there. So I'm adding all of the measurements together and dividing by n. I'll box this. So I'm sure all of you know this, but again, this is good to have when you are making multiple measurements. And then the other thing that I will show you here is standard deviation. Some of you are probably cringing right now because I know that nobody likes calculating standard deviation. By the way, any one of your scientific calculators or graphing calculators will calculate standard deviation for you. You just have to know how to put lists in your calculator. And if you don't, you can always Google it or search it on YouTube. You're going to get a million different links for that. And if you're still having a hard time, you can ask me in office hours. There is going to be just a couple of places where I'm going to ask you to calculate standard deviation by hand. Anyway, so standard deviation, this is basically a way to measure precision, right? So we want to figure out how close these values are to each other, right? Or what's the distribution of these values. So here we use a Greek letter sigma. So this is definitely different from delta. Greek letter sigma, okay? And the way that we're going to do it is we're going to take each value, right? So we have our n measurement. So x with a subscript I, any one or each one of those measurements, we're going to subtract the average value from that measurement. We're going to square that difference, add all of those different values, or add all of those differences, okay? And then divide all of that by n. Now, sometimes when you look up standard deviation, it's actually not going to be n, but it's going to be n minus 1. The difference in statistics between those is whether you're calculating standard deviation of what's called a sample or a population. Let's not worry about that right now. Okay, so let's just leave it like this. So standard deviation, again, you can use n, you can use n minus 1. This is how I'm gonna write it. Okay, and then you're going to take a square root of all of this. Okay, so here is my equation. Right, so it's kind of a complicated process, especially if you have a lot of values. So imagine having to do this by hand if you have 100 values that you measured. No, don't worry, I'm not going to make you calculate standard deviation of 100 numbers by hand. But maybe 5, right? That's not too bad. You can calculate standard deviation of 5 numbers by hand, no problem. Cool thing is, and this you maybe you don't know this from statistics. Cool thing is that you can actually estimate experimental uncertainty based on standard deviation. What I'm going to do is I'm going to go back, and instead of just calling it sigma, I'm going to call it sigma x, as in that's the standard deviation in measuring x. Remember that this is what I'm doing here, is I'm measuring whatever x represents, I'm measuring that value n times, right? So that's why I'm calling this sigma x. That's the standard deviation of all of those measurements of x. So the experimental uncertainty in x would be taking the standard deviation. Don't confuse delta and sigma. They're very similar, and sometimes students tend to confuse the two. So delta is uncertainty, sigma is standard deviation. So anyway, I'm going to take the standard deviation and divide this by square root of n. And again, this is useful for when I'm making this measurement for x, and my goal is to report this value of x as x plus or minus delta x. Right? So for all practical purposes, I should be doing something like this. Now, you can argue that that if you're using some kind of tool, some kind of instrument to make this measurement, then you don't have to go through all of this with delta x, right? If you can already get the delta x, the experimental uncertainty, if you can get that from the tool itself, like taking that smallest division and dividing by 2 or whatever, right? So yes, that is true. You can do that, but maybe in some cases, again, if you have a lot of measurements, maybe even if you had a digital instrument or a computer to make a lot of these measurements, then, especially with the case of a computer, then your better option for figuring out what the uncertainty is would be to go through statistical analysis. And like I said, any one of your scientific calculators, graphing calculators, computers, Excel, for example, will do all of this for you just with a couple of simple commands, simple clicks of a button, or in Excel you would have to type up the command. But again, on a computer, on a calculator, it's much easier than doing this by hand. And I would never ask you to perform statistical analysis like this by hand if we had, 100 measurements. That's just kind of ridiculous, right? But if you had like 3 or 4, 5 values, then there should be no problem for you to calculate the average and the standard deviation of those 3 or 4 or 5 values, and then again report it as value plus or minus uncertainty. So in a great majority of the situations, every time that you perform a laboratory experiment, you should be thinking about uncertainties. And as far as this class is concerned, I may ask you to report the value with uncertainty, or I may not ask you to do that. So in either case, even if I'm not asking you to report the value with uncertainty, you should still be at least, if not calculating it, at the very least thinking about where the errors and the uncertainties can come from for that particular experiment, for that particular setup.